what I'd like to do now is spend the rest of this time talking about one example. And this example, I think, pretty much summarizes everything that we've done up till now. Right, and that's list structure and issues of abstraction and representation and capturing commonality with higher order procedures, and also is going to introduce something we haven't really talked about a lot yet. What I said is the major third theme in this course, meta-linguistic abstraction, which is the idea that one of the ways of tackling complexity in engineering design is to build a suitable, powerful language. You might recall what I said was pretty much the very most important thing that we're going to tell you in this course is that when you think about a language, you think about it in terms of what are the primitives, what are the means of combination, and what are the things that allow you to build bigger things, and then what are the means of abstraction. How do you take those bigger things that you've built and put black boxes around them and use them as elements in making something even more complicated? Now, the particular language I'm going to talk about is an example that was made up by a friend of ours called Peter Henderson. Peter Henderson is at the University of Stirling in Scotland. And what this language is about is making figures that sort of look like this. Right? This is a woodcut by Escher called Square Limit. You sort of see it has this complicated kind of recursive, right? Sort of recursive kind of figure where there's this fish pattern in the middle and things sort of bleed out smaller and smaller in self-similar ways. Anyway, Peter Henderson's language was for describing figures that look like that and designing new ones that look like that and drawing them on a display screen. There's another theme that we'll see illustrated by this example, and that's the issue of what Jerry and I have already mentioned a lot, that there's no real difference in some sense between procedures and data. And I hope by the end of this morning, if you're not already, you will be completely confused about what the difference between procedures and data are, if you're not confused about that already. Well, in any case, let's start describing Peter's language. I should start by telling you what the primitives are. This language is very simple because there's only one primitive. The primitive is not quite what you think it is. There's only one primitive called a picture. And a picture is not quite what you think it is. Here's an example. This is a picture of George. The idea is that a picture in this language is going to be something that draws a figure scaled to fit a rectangle that you specify. So here you see in faint lines this outline of the rectangle. That's not really part of the picture. But the picture, you'll give it a rectangle and it will draw this figure scaled to fit the rectangle. So for example, there's George, and here this is also George. It's the same picture, right? Just scaled to fit a different rectangle. Here's George as a fat kid, and that's the same George. Right? It's all the same figure. All of these three things are the same picture in this language. I'm just giving it different rectangles to scale itself in. Okay, those are the primitives. That is the primitive. So let's start talking about the means of combination and the operations. There's, for example, an operation called rotate. And what rotate does is if I have a picture, say a picture that draws an A in some rectangle that I give it, the rotate of that, say the rotate by 90 degrees, would, if I give it a rectangle, draw the same image, but again scaled to fit that rectangle. So that's rotate by 90 degrees. There's another operation called flip. I can flip something either horizontally or vertically. Right, so those are sort of operations, or you can think of those as means of combination of one element. I can put things together. There's a means of combination called beside. And what beside does, it'll take two pictures, let's say A and B, and by picture I mean something that's going to draw an image in a specified rectangle. And what beside will do, I have to say beside of A and B, beside of two pictures and some number S. And S will be a number between 0 and 1. And beside will draw a picture that looks like this. It'll take the rectangle you give it and scale its base by S. Say S is 0.5. And then over here it'll put the picture, the first picture, and over here it'll put the second picture. Or for instance, if I gave it a different value of S, if I said beside with a 0.25, then it would do the same thing, except the A would be much skinnier. So we draw something like that. Okay, so there's a means of combination beside. And similarly, there's an above, which does the same thing, except it puts them vertically instead of horizontally. Well, let's look at that. Right, there's George and his kid brother, which is constructed by taking George and putting him beside the above, taking the empty picture, and there's a thing called the empty picture, which does the obvious thing, putting the empty picture above a copy of George, and then putting that whole thing beside George. Here's something called P, which is, again, George beside, flipping George, I think horizontally in this case, and then rotating the whole result by 180 degrees, and putting them beside one another with the basic rectangle divided at 0.5. Right, and I can call that P. And then I can take P and put it above the flipped copy of itself, and I can call that Q. Notice how rapidly that we've built up complexity. Just in 15 seconds, we've gotten from George to that thing Q. Why is that? How are we able to do that so fast? The answer is the closure property. See, it's the fact that when I take a picture and put it beside another picture, that's then again a picture that I can go and rotate or flip or put above something else. Right? And when I take that element P, which is the beside or the flip or the rotate of something, that's again a picture. Right? The world of pictures is closed under those means of combination. So whenever I have something, I can turn right around and use that as an element in something else. So maybe better than lists and segments. That just gives you an image for how fast you can build up complexity because operations are closed. Okay, well, before we go on with building more things, let's talk about how this language is actually implemented. The basic element that sits under the table here is a thing called a rectangle. And what a rectangle is going to be, it's a thing that's specified by an origin. That's going to be some vector that says where the rectangle starts, and then there's going to be some other vector that I'm going to call the horizontal part of the rectangle, and some other, and another vector called the vertical part of the rectangle. And that specifies those three pieces of elements: where the lower vertex is, how you get to the next vertex over here, and how you get to the vertex over there. Three vectors specify a rectangle. Now, to actually build rectangles, what I'll assume is that we have a constructor called makeRectangle, or makeRect, and selectors called horiz and vert and origin that get out the pieces of that rectangle. And, well, you know a lot of ways you can do this now. You can do it by using pairs in some way or other, standard lists or not. But in any case, the implementation of these things, that's George's problem. It's just a data representation problem. So let's assume we have these rectangles to work with. Okay. Now, the idea of this, remember what's got to happen. Somehow we have to worry about taking a figure and scaling it to fit some rectangle that you give it. That's the basic thing you have to arrange that these pictures can do. How do we think about that? Well, one way to think about that is that any time I give you a rectangle, anytime I give you a rectangle, that defines, in some sense, a transformation from the standard square into that rectangle. Let me see what I mean. By the standard square, I mean something which is a square whose coordinates are 0, 0, and 1, 0, and 0, 1, and 1, 1. And there's some sort of the obvious scaling transformation which maps this to that and this to that and sort of stretches everything uniformly. So it would take a line segment like this and end up mapping it to a line segment like that. So some point xy goes to some other point up there. And although it's not important with a little vector algebra, you could write that formula. The thing that xy goes to, the point that xy goes to, is gotten by taking the origin of the rectangle and then adding that as a vector to, well, take x, the x coordinate, which is something between 0 and 1, multiply that by the horizontal vector of the rectangle, and take the y coordinate, which is also something between 0 and 1, and multiply that by the vertical vector of the rectangle. That's just a little linear algebra. Anyway, that's the formula, which is the right obvious transformation that takes things into the unit square into the interior of that rectangle. Okay, well, let's actually look at that as a procedure. See, what we want is the thing which tells us that particular transformation that a rectangle defines. So here's the procedure. I'll call it coordinate map. Coordinate map is a thing that takes as its argument a rectangle and returns for you a procedure on points. Right? So for each rectangle, you get a way of transforming a point xy into that rectangle. And how do you get it? Well, I just, writing in Lisp what I wrote there on the blackboard, I add to the origin of the rectangle the result of adding, I take the horizontal part of the rectangle, I scale that by the x-coordinate of the point, I take the vertical vector of the rectangle, I scale that by the y-coordinate of the point, and then add all those three things up. That's the procedure. That is the procedure that I'm going to apply to a point. And this whole thing is generated for each rectangle. So any rectangle defines a coordinate map, which is a procedure on points. Okay. Right, so for example, George here, my original George, might have been something that I specified by segments in the unit square. And then for each rectangle I give this thing, I'm going to draw those segments inside that rectangle. How actually do I do that? Well, I take each segment in my original reference George that was specified, and to each of the endpoints of those segments, I apply the coordinate map of the particular rectangle I want to draw it in. So for example, this lower rectangle, right, this George is a fat kid rectangle, has its coordinate map, and if I want to draw this image, what I do is for each segment here, say for this segment, I transform that point by the coordinate map, transform that point by the coordinate map, that'll give me this point, and draw the segment between them. Right, that's the idea. Right, and if I give it a different rectangle like this one, that's a different coordinate map, so I get a different image of those line segments. Well, how do we actually get a picture to start with? I can build a picture to start with out of a list of line segments initially. Here's a procedure that builds what I'll call a primitive picture, meaning one I sort of got that didn't come out of the side or rotate or something. It starts with a list of line segments. And now it does what I said. What's a picture have to be? First of all, it's a procedure that's defined on rectangles. What does it do? It says for each, this is going to be a list of line segments. For each segment, for each S, which is a segment in this list of segments, well, it draws a line. What line does it draw? It gets the start point of that segment, transforms that by the coordinate map of the rectangle. That's the first new point it wants to do. Then it takes the end point of the segment, transforms that by the coordinate map of the rectangle, and then draws a line between them. Let's assume draw a line is some primitive that's built into the system that actually draws a line on the display. Right, so it transforms the endpoints by the coordinate map of the rectangle, draws a line between them, does that for each S in this list of segments. And now remember again, a picture is a procedure that takes a rectangle as argument. So when you hand it a rectangle, this is what it does. Draws those lines. Right, so there's how would I actually use this thing. Just to make it a little bit more concrete. Right, I would say, for instance, define R to be make rectangle of some stuff, and I'd have to specify some vectors here using make vector. And then I could say define, say G to be make picture, and then some stuff. And what I have to specify here is a list of line segments, right, using make segment. And make segment might be made out of vectors, and vectors might be made out of points. And then if I actually wanted to see the image of G inside a rectangle, well, a picture is a procedure that takes a rectangle as argument. So if I then called G with an input of R, that would cause whatever image G is worrying about to be drawn inside the rectangle R. All right, so that's how you use that.